Okay, thank you very much. Good afternoon, everyone. I hope everyone can hear my voice. So I welcome you all in the third session of Extragalactic Astronomy, third parallel session. In this session, we have 5 talks, and we'll start with Shabnam's talk. Shabnam, I'll give you a warning around 25 minutes or 24 minutes. You have 30 minutes, and we also take a few questions. I'll glad if you finish by 25 minutes or so. You can start sharing your screen, and Shabnam will be talking about the investigation of prompt emission of GRBs for the identification of central engine and viewing angle of the jet. Shabnam, you're on.
Okay, so I think I just need to quit and come back. I think that's just give me a second.
Sure.
उनको और एक बार बोलना पड़ेगा जो शबनम मैम आए मतलब उनको फिर से को-होस्ट बनाने के लिए क्योंकि उनका टॉक है। हाँ, एक बार दीवान फोन करके उनको बोल दिया। क्या बोला उन्होंने? वो कह रहे थे कि गूगल लिंक का जाएगा ना, वो अपने में खुद खुल ले, जैसे हम नहीं खोल सकते ना जब तक वो साइन इन नहीं करेंगे उसमें। को-होस्ट बनाना पड़ेगा।
Shabnam, just wait for 1 minute because the host will make you the co-host now. Then you can share the screen. Just wait for 1 minute. Ma'am, I think now you can share the screen. You are the co-host now.
Yeah, I hope you can see my screen.
Yes, Shabnam, we can see your screen. Please make it full screen, I believe.
Okay. I hope you can see.
Yes, we can see the full screen mode.
Yeah. I think it moves, right?
Yes.
Slide.
Please
Okay.
come on.
Yeah. So hello everyone. Good afternoon. So today I'll be talking about basically how to use the study of the prompt emission of gamma ray bursts, basically to identify the central engine properties as well as the viewing angle to the prompt emission jet. So it is 2 projects that we have done, and I'll be basically talking about them. So as we all know, gamma ray burst is one of the brightest events that happens in the universe, and the emission is mostly projected in the form of a jet that comes out, as you can see in this illustration. And therefore, now the major picture or the basic framework under which we try to understand the gamma ray burst is basically called as the classical fireball model, which I am describing particularly here on the screen. So irrespective of what the progenitors are, whether it is the merger of 2 compact objects like 2 neutron stars, or if it is a neutron star or a black hole, or if it is a core collapse of a very massive star towards the end of its life, what at the end happens is that you form a very compact object like a black hole or a magnetar, and it basically starts accreting the matter surrounding it, and you produce a very powerful jet which actually pierces through the matter that surrounds it and comes out. So this is what you see. So basically the outflow in the beginning, it's in the form of a fireball. As the name suggests, it's very dominant in radiation, and as a result of which it pushes the material outwards, accelerating the matter that is present to very high velocities close to the speed of light. And that is what we see as a jet. So initially in the beginning, the outflow is actually quite dense, and it's present in a very small volume. As a result of it, whatever the photons or radiation that is present basically undergoes a large number of scatterings and finally thermalizes. And as it expands, the volume increases, so at the density of particles decreases, and at some point the radiation gets decoupled from the plasma, and this is what we refer to as the photosphere. So you generally expect to see a thermal emission coming from the photosphere. Later on, you can imagine this outflow in the form of various shells of matter of different energies and masses being ejected. And a fast moving shell can go and crash into a slow moving shell, and this energy, the differential kinetic energy between these two shells would get dissipated, and in the shocks that are created, the electrons can get accelerated to very high velocities, which eventually radiate via non-thermal emission processes like synchrotron or inverse Compton scattering or so. So this and this might appear as I said, something very non-thermal in spectral shape. So this basically composes of what we call as, or what we see as, the prompt emission, and the jet further goes on and crashes into the interstellar medium, which basically produces what we see as the afterglow, which can be observed in multiple wavelengths starting from radios till gamma rays. So in this talk, we'll be only focusing largely on the prompt emission part, how we use prompt emission as a diagnostic to look at one, that is the viewing geometry. So as you can see, the GRB jet is, as it is a jet, that is, it is have only a particular solid angle. So therefore the viewing, how you view the jet would definitely determine the kind of spectra you will see. And also we use the prompt emission as a diagnostic to shed some light on what could be the central engine that gives rise to this powerful outflows that we see. So one of the most celebrated events that have happened in the recent years is basically the coincident detection of gravitational and electromagnetic waves that particularly happened in concurrent to the short GRB 1708-17A, which marked the beginning of the multi-messenger era in astronomy and astrophysics. Now, why it was so spectacular was because one, definitely we saw gravitational waves that is there, but this merger of binary neutron stars, till then it was a hypothesis that they were produced by the merger of two compact objects, but this actually provided a confirmation of it. And this event basically has four main observable parts to it. One is, as it merges, it spirals down and comes to a merger, it produces the gravitational waves, and also and then as it comes closer, it tidally disrupts each other and spews out a lot of neutron-rich matter, which finally gives rise to heavier elements, which gets nuclear synthesized. And these heavier elements then undergo radioactive decay, and a glow is produced, which is called as a kilonova, which is isotropically emitted, as illustrated, as you can see. And then you also have this prompt gamma ray emission with the short GRB, and then you also have the standard afterglow, what we expect to see. So what was spectacular about 1708-17 was that we were able to see all the four observable parts of this event. And this is the time arrow of this event. As you can see below, onto your left, is on the bottom panel is the gravitational wave detection which happened, which marks the trigger time 0. When the spiraling happens and when the frequency rapidly kind of increases. And after nearly 2 seconds later, an electromagnetic counterpart was detected in the gamma ray detectors, both Fermi and integral. And nearly several hours later, near 12 to 14 hours later, we were also able to detect first a blue emission and later which moved into red, which basically marked the observation of kilonova that was observed. And later, nearly 9 days later, we were able to first see the first signal in X-rays that was observed, which marked the beginning of the afterglow. And as you can see on the right bottom corner, what we are seeing is the afterglow light curve, which was observed in various multiple frequencies. And what was interesting was that this afterglow light curve was not typical of what we generally see in GRBs, where we generally used to see only a decaying light curve. Whereas here, the afterglow light curve was increasing with time, and it peaked around a few 100 days, and then it turned over. So this was a completely atypical behavior of the GRB afterglow that we have seen till date. So what we have learned so far of this event, apart from the progenitor confirmation that we had, one important thing that we understood in this case was that the GRB was viewed off axis. And this confirmation came from two things. One was the gravitational wave signature that was detected, which also told that there was an inclination to the event that we have seen. And also the atypical afterglow behavior that we have seen, that is the rise in the flux of the GRB with over such a long period of time, also indicated that we have viewed this jet actually significantly off axis. So then it gave rise to the question of what could be, if it is viewed off axis, that means we are able to see something, then it has this profile of rise that we are seeing has something to do with the kind of jet structure that we are looking at, or the other proposed idea is that it is surrounded by a cocoon. So that means whatever we see as the prompt emission in the GRB also will have a lot of dependence on the kind of dynamics what the jet has along that line of sight of the observer. And that means it can also vary with the dynamics the dynamics of the jet can vary with angle from the axis. So apart from that, there have been heavier elements have been detected, such as strontium was detected in. We understand that these kind of events can give rise to heavier elements, and also there's been hints of softer equation of state for neutron stars. But what has been interesting for me is the part that I've highlighted, that is, the jet can be viewed off axis, because typically, generally, when we study GRBs, we generally often assume that the jets or the GRB that we have seen is on axis, and that is how we generally do our all calculations or inferences on it. But the important part here was that the jet can be viewed off axis and it can have some structure to it. So in this scenario, first, we actually looked at a sample of short GRBs, which I'll come to it. So, but I wanted to draw your attention to, when we look at prompt, what we're seeing is certain radiation gamma rays. So one thing we look at is the spectrum. So when you look at radiation, the first question that we ask is, from where in the jet outflow is this radiation produced? So if you remember the fireball model, one is the photosphere, or it can be an optically thin region above the photosphere. So the photosphere is the region, the deepest region in the outflow from where you can see something. And as I said already, it looks thermal in nature. Particularly what I want to focus you on about is, when you look at the thermal spectrum, it has a very steep, hard, low energy spectral index. Whereas in comparison to the non-thermal emission like synchrotron, if you look, which is produced when relativistic electrons gyrate through the magnetic fields, from a distribution of electrons, the synchrotron emission would look something very broad like this. And it has, in relative to thermal spectrum, if you look, this low energy part of the synchrotron spectrum is much, much softer. So, and as you know, a GRB spectrum is generally modeled using a phenomenological function called as band, which is nothing but two power laws smoothly joined. As you can see in the upper panel, it's just two broken power laws, which is smoothly joined at the E break. And what we use as a diagnostic is the low energy power law index, which is denoted as alpha. So what we did was, if you just look at the alpha and beta distribution of short GRB, that is for the time integrated spectra for Fermi detected GRBs, what we have shown in blue is the distribution for short GRBs, and in green is for that long GRBs. And this vertical dashed line that shows is the line of death of synchrotron emission, which marks alpha is equal to minus 0.67. So anything beyond that, greater than minus 0.67, cannot be produced by a typical synchrotron scenario. So this basically, nearly 61% of the short GRB spectra of the sample that's still observed by Fermi is actually inconsistent with synchrotron. And it has a very hard low energy power law index. And among the 61% of short GRB, we looked at how is its high energy part. That is the beta part. And we found that nearly 69% of those spectra were actually quite hard also. It had beta indices which were much softer than minus 2.5. That means it's very steep. So that means if you just look at in general, that means we're talking about a spectral shape which is quite hard at the low energy part of the spectrum, and at the high energy part it's very steep. That means it has a kind of a hard narrow kind of spectrum, and it point towards that it's mostly originating from the photosphere. So keeping this as the motivation, and also taking into the point that a jet can be viewed off axis, what we looked through was that there was a study done by Ludman et al. 2013, where they basically looked at a structured jet model where the emission was dominantly coming from a non-dissipative photosphere. So that means the emission from the photosphere would be simply a black body if we viewed it on axis. So basically the jet structure is what I'll explain here, what you see on your left side. So we have a core region which is marked by theta C, and then the jet opening angle is theta J. Is within the theta J that you have the energy of the jet that is injected. And the Lorentz factor profile of this jet is such that it remains constant within the core of the jet, and beyond the core it basically decreases as a power law such that gamma goes proportional to theta to the power minus p. And the luminosity of the burst, the energy injection basically remains a constant within the entire theta J. So this was the jet profile that was studied in Ludman et al. 2013. It's a simplistic case. And the motivation of why it needed to be a power law kind of profile was all taken from the hydrodynamical simulations that were done by various groups, which looked at how the jet interacts with the stellar cover medium as it comes out. And so in this case, what happens is if you view the jet on axis, then your Lorentz factor remains a constant within the jet during that. So therefore, whatever your Doppler boost, you will more probably see a black body, as you can see here in the plot. But when you go off axis and you view it at a certain angle, theta V, but still within theta J, what you will see is that it will be within your view cone of 1 over gamma. You will be seeing, because the Lorentz factors is continuously decreasing, that means the Doppler boosted temperature in the observer frame will be of various values. So there will be a decreasing, it will be a superposition of many black bodies with a decreasing temperature profile. So therefore you will be seeing a multicolor black body, and the low energy part of the spectrum would get much softened. And that is what we can see in the plot on the right side. So we basically used an empirical or a more phenomenological function of a multicolor black body, which basically has a dependence of temperature profile like T to the proportional to R to the power minus zeta. And if zeta is very, very hard, that means you are more closer to a black body. And if it gets softer, a smaller values means your low energy part has certain profile of temperature, and it looks much broader than that of a black body. Now, this is what you're talking about, jet structured thing. So what we did was we basically went and we studied a sample of short GRBs with a multicolor black body. Now, before we look at the results that we get, I also wanted to put in perspective the alternate model that is also existent in the community, which is the cocoon jet model. And it's a cocoon jet model. What basically it also, there's not much of a huge difference between these two things, but it's just again that what you have is a surrounding certain medium which is only mildly relativistic, only have a few gamma, but you have a jet and at the center which is moving at very high relativistic speeds. And because it's first of all, it's mildly relativistic and it has higher opacity. What the expected spectrum from there is more thermal or Comptonite spectrum. So you can see the similarity. So if you're seeing a thermal spectrum, you can also ask a question if it can be coming from a cocoon or not. Okay, so this is what we are going to look at. So there was a study in 2017 that was conducted by Lazati, who basically looked at this cocoon jet model, and he kind of showed what amount of isotropic equivalent energies that you can see. For example, there's various components that has been plotted. In red, what you're seeing is the total radiated energy that you can see, and in green is if it is completely thermal. And if it is in magenta, what you're seeing is if it is a Comptonized spectrum. And this isotropic energy that you that can be expected to be seen across the off-axis angle is what is being plotted. So for in the case of, at an angle what I've shaded around, let's say from close to 15 to 45 degrees or so is what I've plotted. And you can see that if you're seeing a thermal spectrum, more like a thermal spectrum, you can see that the expected isotropic equivalent energy is definitely less than 10 to the power 49 ergs if it is coming from a cocoon. The maximum, the peak photon energy that you can expect to see from the photosphere of a cocoon is basically less than 10 keV, as you can see here in the plot. So these are certain things to just keep in mind before we look at the results that we get when we analyze the prompt emission spectra. Okay, so we analyzed basically 39 short GRBs with known redshift that were observed either by Fermi or by Swift. And this is basically the distribution plots of both redshift and isotropic energies that we have shown here. Now, this is the interesting one, that is where we plot the peak temperature of the multicolor black body that we got versus the alpha. And interesting here is the zeta, if you remember, if it is very strong, which is much, if it is in red, what you're talking about is very large values, that is the spectrum is more closer to that of a black body. And that is what I've highlighted here. And you can see that their values, the peak temperature values, are all kind of greater than 10 kV. Okay, and the other is that there is no particular correlation that we see with the low energy spectral index and as well as the peak temperature. So there is no energy window bias of whatever measurements of hard alpha that we are talking about here. So we can kind of trust the values of alpha that we are seeing here. And other is we looked at the isotropic energy. And also for all those very, burst which had a thermal kind of spectra, we particularly look, they all had values greater than 10 to the power 48 ergs. So, so there seems to be like this because, and we are kind of looking at a generic picture of things. So as you can see that their characteristics of this thermal GRBs are not very different from the other GRBs which have a more broader or more multicolor black body spectral shapes. So it seems that they are not they need not have any special class of origin, or maybe it's not particularly from a cocoon or so. So what we have interpretations that we have done is basically within a structured jet model. That's what I've explained earlier, that is the Lundman model. So the Lundman model, since they simulated the kind of spectra that you can see at different viewing angles, and what they showed was that with alphas, if it is greater than minus 0.5, or the cases wherever in the afterglow we have seen a jet break, we have classified them as, or we identified that those cases are GRBs which are viewed within the jet core. And the others are the cases where they are viewed outside the jet core. So when we look at the sample, we understand that 57% of the sample that we have taken is viewed within the jet core. And we also estimated the index of what this profile should be, and it showed a tentative like bimodal like Gaussian fit, and with the p-value roughly between 1.3 and 2.23. And this correlation is also predicted in Lundman's model, where the alpha and the low energy power law index and the profile index, how they should be correlated, and so. And
Shabnam, you have 6 to 7 minutes.
Okay. Okay, so so we also estimated what is the median of the angle at the core, that is 3 degrees, and also we looked at the jet opening angle, which also we found out 10 degrees. So the interesting thing was that is that we kind of predict what kind of rate of short GRBs it should be that can be coincidentally detected with LIGO, that is with very bright emission, and it would be around 0.19 to 2.87 per year. And next, I'll just go through. We'll also looked at to understand what is the central engine of the GRB, which is basically magnetar, or if it's a Kerr black hole. And it is because the magnetar model has basically an upper limit to how much of energy it can produce, and it's around 3 times 10 to the power 52 ergs. And this magnetar rotational energy can be divided, will be channeled into 3 main parts: it's a gravitational wave, the relativistic jet, and the magnetospheric wind. So considering equipartition, we can say that the maximum energy that can be channeled, it will be around 10 to the power 52 ergs. So using this as a diagnostic, we analyze the entire prompt emission spectra of all 11 years of that's been detected by Fermi. And we basically identified 105 hyper energetic GRBs, which had isotropic energies greater than 3 times 10 to the power 52 ergs. Then we did the beam correction, that is, we corrected for their opening angles, and we identified 8 long GRBs which actually exceeded this limit of 10 to the power 52 ergs. So these GRBs certainly have black hole as their central engine. And once we and also we looked at the X-ray afterglow light curves of these, and we did not find any signature for a plateau or a shallow decay or a steep decay later in time or so. So which kind of more supports the fact that the central engine can more likely be a black hole itself. And since we know now this is a black hole, and assuming Blanford-Zenith mechanism as the process of extracting the relativistic jet from it, and using the respective proportions of energy transfer that can happen, we estimated what could be the masses of these black holes, and we found that it would range between 2 to 60 solar masses, and that is what is shown here in red diamond markers. And as you can see, the shaded region, what I've shown here, is called as the mass cap region, which basically tells you the region where we have it's 2 to 5 solar masses, where we actually have not identified events where it can be, we don't know if it can be a massive neutron star or if it is a very lighter black hole that we have seen. So we have not been able to confirm this. So for example, for gravitational wave event 1908-14, one of the binary components actually had a mass which lied in this region, and we are not sure of its nature. So in this study, what we showed was that some of the confirmed black hole central engine of GRBs actually can have masses which can lie in this mass cap region, and therefore it can be probable that this this component that we have observed in gravitational wave event can most likely be a black hole. So to just summarize, the study of prompt emission can help us reveal to some extent what is the viewing angle geometry of the jet. The current study that we have done is only particularly limited to a particular kind of a profile that we have done. And this is more done in an I would say a bit of an more approximate manner. And one thing that we can do in future is like test it with different other jet profiles, and at the same time is to do direct physical model testing. That is also something that can be done. And also, as I said, the energetics can give us some diagnostic as to how to identify what is the central engine. And these informations can become very crucial when we have now concurrent detections in gravitational wave and multi-wavelength observations, when we can then enable us to zero it down to what could be the where it can help us make robust inferences regarding both the viewing geometry as well as the central engine properties. So yeah, with this I'll end, and I'll happy to take questions.
Thank you, Shabnam, for a very interesting talk. So now forum is open for a few questions. So if there is any question from the hall, I would just request them to ask. If there are no more questions from the from the hall. Then probably I can take a few questions from the online audience. Yeah, Varun, please go on.
Yeah.
Hi.
Yeah.
Yes. Shabnam, nice talk.
Yes.
Observationally, since you have already looked at all these 10-year samples and so on, what are the observations that you would need to figure out these things?
Okay, is both the viewing geometry and central engine. Okay, so in terms of central engine, the diagnostic that we have used is just the energetics. So the main important thing for us would be to identify that to make a correct volumetric energy estimate. So yeah, so that would be the most important thing, to actually see that the energy estimate or the spectral modeling that we have done is robust enough to all the higher whatever, because more wider the energy range you have, that's the best that we can see. So so mostly here the 8 cases that we have seen, excepting one, all had very bright lat emissions. So they were seen to certain several GB energies. So so in the modeling we have taken all that into consideration. Therefore to certain extent we are kind of very sure about the volumetric flux that we have estimated, and therefore the energetics would be much better. Yeah, so that would be one important thing. And another aspect is that that the viewing of the jet can also be an important factor in the central engine estimate itself. That is, how do we know that if we have viewed the jet on axis? Because the project that we did, we assumed that it is all on axis. One thing is that because it's already very, very bright, as I said, it's already the isotropic energies are 3 times 10 to the power 52 ergs, and all the 8 cases where we have identified it's definitely above 1 times 10 to the power 52. So if you assume that we have seen this off axis, that means your true energy would have been even more greater. So it would still act in favor of the diagnostic that we are trying to do. But yes, so but that would actually affect the correct estimate of the energetics. So estimating the energetics is the most important thing. And the viewing geometry part, here in the work that we did, we have combined 2 things. So one is, using the prompt emission part, we have just classified from the model that it can be either viewed within the jet core or is it viewed outside the jet core. Then the later estimates of viewing angle and things like that, we have done it combined using the X-ray afterglow data that has been observed. So yeah, it's a combination of certain things, but what I'm saying is that there can be certain info. So if you're doing a direct model testing, that is, I can test this Lundman et al. Model directly with the data, where this theta v and things would be one of the fit parameters, then I can get that value. Currently, we have not done that. We have only kind of used an empirical function to just model the kind of we estimate multicolor black body, and that is what we are expecting to see, and we have done the inferences based on that. But one way forward would be that we directly test the physical model with the data directly. There, this viewing angle and theta j and things can be one of parameters of your fit. That was possible. Yeah.
Thank you, Shabnam. As we are going little late, I would, if there is any very quick question and quick answer to that, I will take it. Otherwise, probably we'll move forward.
Hello. Hello.
Yes.
Shabnam. I have one question. Dimple this
Please.
side. I have a question regarding the estimation of true energetic of the burst. So how you calculated the jet opting angle, because you will need the achromatic, you will need to estimate the achromatic jet break. So you need the multiwavelength data for that. So in case of short GRB, in most of short GRB, there is not rich data. So do you model the data, multiwavelength data, to estimate the jet wake and jet opening angle?
Yeah, so in the case of the short GRB project that you're asking, there the jet opening angle, the theta j that we are thinking, as I said, there is only a certain class of GRBs which are viewed on axis is what we try to estimate theta j. So wherever there we have seen a jet break, we have taken that values. Otherwise, we have used a constraint of what could be the maximum angle that a jet should have, so that it can successfully come out of a given the certain energetics, and what could be the angle that solid angle that jet can have, so that it successfully comes out of the stellar matter it has. So there is a simulation study that is being done based on that. So we have used that as an guideline to get what could be the possible angle. So there, see, in that study, we have not estimated one single value. We have given a probable range, a minimum and maximum angle limits. Limits are what we have actually worked out. We are not worked out a single particular value in that.
The true energetic that you have calculated will also be the limits.
If you are asking the second project on central engine where burst energetics are done, we have taken all the values.
Sorry, as we are getting late,
Yeah.
I think we can take the question and answer on Slack. Thank you very much.
Yeah, thanks.
For the wonderful talk. Now we'll move on. I request.
Sir, actually, Dhrubojyoti has sent one video lecture. So can I play it now?
Yes. So next talk is by Dhrubojyoti Sengupta. He will be talking about X-ray vision on local obscured AGN. And as probably he may not be present, we'll run the video. And in case if he is in the audience, probably we may have a few questions at the end. If he is not, then we'll have the video, and probably audience can contact with him through Slack, or maybe we can write to him.
Hello everyone. Today I will talk on X-ray analysis.
We are not seeing the screen.
Yeah, just 1 second, sir. It's almost done.
Hello everyone. Today I will talk on X-ray analysis of low redshift obscured active galaxies. The question is why we need to study obscured AGN from X-ray perspective. Hello everyone. Today I will talk on X-ray analysis of low redshift obscured active galaxies. The question is why we need to study obscured AGN from X-ray perspective. The answer is to understand cosmic X-ray background radiation. Since last 60 years, through a series of deep and wide surveys of the sky by X-ray telescopes, we found that AGNs are mostly responsible for CXB. We found that CXB peaks around 20 to 30 keV, and obscured AGN has about 40% contribution in that. The obscured AGN with column density over 10 to the power 24 per centimeter square is called Compton thick, or CT AGN, which itself contributes to 20% at the peak. Now, at low redshift, that is below 0.1, the observed fraction is only about 5 to 10%. Whereas the CXB population synthesis models predict that the fraction of CTAGN will be around 20 to 50%. Thus, to narrow this large gap between observation and model predictions, we came down to hunt the missing population. Now, along with this issue, we know that obscured AGN is a phase in the picture of galaxy merger paradigm and carries information about host galaxy environment. Also, the orientation of the obscuring median, which is commonly known as torus, connects with the AGN unification model. So overall, studying obscured AGN helps us to understand the structural formation and evolution of the universe, along with dealing with CXB problem. This is a very familiar picture of an AGN with a supermassive black hole at the center surrounding by accretion disk. This is the obscuring torus consisting of molecular gas and dust. On the basis of presence of jet and orientation with our line of sight, they have different identifications. Here we are mostly concerned about non-jet type 2 AGN. Let's now discuss briefly about the AGN composition and its spectral components. This is a very crude representation of the scales in AGN, and this one is a standard AGN spectral energy distribution, or ACD, for type 1 AGN. The accretion disk converts gravitational energy of the supermassive black hole to a multicolored black body spectra, which peaks in optical UV. The hot plasma, having temperature about 10 to the power 8 to 9 Kelvin, often called corona, present very near to the accretion disk, is responsible for producing X-ray as the power law in the ACD. On this context, let's see how X-rays are cooked inside an AGN. So a part of the thermal radiation coming from the accretion disk strikes the ionized corona, and through series of inverse Compton scattering, the photons are upscattered and comes out isotropically as power law component. Almost half of these photons return back to interact with the accretion disk and the obscuring material by photoelectric absorption and reflection, and eventually comes out as a reflection component, making a hump around 20 to 30 keV. Keep in mind the similarity of this hump and the CXB peak around this 20 to 30 keV. Also, along with this, we can notice strong signatures of fluorescent lines as iron K alpha and K beta around 6.4 keV and 7 keV respectively. The photon index for the power law is estimated to lie between 1.8 to 2, but with observational data, we see that it can vary from 1.5 to 2.2. Anyways, this thermal and X-ray emission from the center is absorbed by the obscuring torus and re-emitted in the infrared band as shown in the ACD. These polar dust and torus are identified as obscuring materials, which are composed of dust grains and gas. Dust grains are responsible for UV to infrared extinction, whereas metals in the gas absorb the X-rays. Now, on the basis of column density of these obscuring materials, we can classify AGN as Compton thin and Compton thick. Our work is focused on CT AGN, which has column density over 10 to the power 24 per centimeter square. So, let's see how we study CT obscuration. Firstly, column density distribution, which varies as we move away from the horizontal axis. It also depends on the shape of the torus and inclination angle. So we define two parameters, inclination angle and covering factor. Inclination angle is the angle between the observer's line of sight and symmetry axis of the torus, whereas the covering factor is the fraction of the sky blocked by torus as seen from the nucleus. Therefore, this is how the AGN ACD changes with column density. Here you can see for column density 10 to the power 22, the power law dominates in both soft and hard X-ray part. With increase of column density over 10 to the power 24 per centimeter square, the X-ray emission below 10 keV is completely suppressed and reflection component starts to dominate over power law. You can also notice strong iron K alpha line, which generally have equivalent with over 1 keV for CT AGN. So this is how a CT AGN ACD looks like in X-ray regime. Now let us discuss a bit about the accepted type of torus models. It is generally either smooth or clumpy. As by the name, smooth distribution is given for uniform distribution of clouds, whereas clumpy models suggest that the different radii have different cloud density, forming clumps of non-uniform distribution of the cloud. To analyze these models, we use expect code of coupled configuration of my torus for smooth model, and for clumpy, we have decoupled configuration of my torus, borus, and X-clump. Though my torus and borus follow smooth distribution, we can tune their parameters to check the clumpiness. A fairly new code, X-clumpy, is explicitly written for clumpy scenario, but we haven't used it yet in the work. So let's introduce briefly to the my torus and borus models. My torus is modeled like a donut distribution composed of three components: direct, scattered, and fluorescent lines. In coupled configuration, all of them are tied together, whereas for decoupled parameters, they are left free to vary. So by comparing the column density from direct and scattered components separately, we can estimate the clumpiness of the cloud. On the other hand, Boras also calculates clumpiness for a continuous distribution of clouds from nucleus to torus, as you can see in the picture. As an extra, it can calculate covering factor and inclination angle also. We use both the models for our analysis to check the consistency of these results. Now, let me introduce you to all about the CLAIMS and INAV CTAGN program, a research collaboration of which I am also a part of. The detail of our research and publication can be found in this website. In short, our ultimate goal is to obtain an almost complete census of heavily obscured AGN in the local universe within energies 15 to 150 keV. In the current project, we are analyzing 55 local CTAGN candidates from the 105-month volume-limited SWIFT batch samples with archival NewStar data in hard X-ray. From them, the analysis of 48 sources has been published. I am working on the last 7 unpublished sources. I am analyzing these CTAGN candidates through X-ray analysis in both soft and hard X-rays, along with mid-infrared fitting. For soft X-rays, that is below 10 keV, we have Chandra and XMM Newton data. For hard X-ray, that is above 10 keV, we had both SWIFT-BAT and NewStar data, but SWIFT-BAT is a coded mask telescope, which has large collecting area, high background, resulting in low sensitivity to faint sources like ours, giving large uncertainty while measuring column density and other parameters also. On the other hand, NewStar is a grazing incidence telescope covering a range from 3 to 79 keV with small and focused field of view, low background, and excellent sensitivity. Thus, we have a better estimate of column density and other parameters with NewStar data. So for our work, we are using NewStar data for analysis and used SWIFT-BAT data for selection of the candidates. I analyzed these 7 sources from Palermo SWIFT-BAT catalog, which you can find in the O et al. Paper. Today, due to lack of time, I will show the most interesting results of these 3 CTAGN candidates and briefly mention about the rest in the end. So for this source, at 0.044 redshift, we have excellent spectral counts in both soft and hard X-ray for 3 telescopes. Including this one for all other candidates, we selected the sources with 30 arcsecond and extracted the spectra through data reduction and data processing for each of the telescopic observations. And this is our fit on the data. You can see for my torus and boros, the reduced chi-square fit is almost near to 1. Even the column density is also consistent for both the models. Also to notice that average column density is about 10 times than the line of sight column density, signifying a clumpy distribution. But both falls below CTAGN threshold. Also, the equivalent width of iron K alpha line comes much lower than 1 keV. On the other hand, Boras gives the best fit of covering factor 1, showing that the source is heavily obscured. So for this source, we can conclude that it is a Compton thin AGN, which is heavily obscured by clumpy torus clouds. Very interesting to note that this source was marked as a CTAGN in Ricky et al. 2015. The reason why our result is significantly different from that paper is because they used SWIFT XRT and BAT data. Due to poor photon statistic, it overestimated the power law and photon index, giving different results from us. For the next source, we have only XMM Newton observation in soft X-rays with excellent photon counts. Even for hard X-rays, combining the NewStar observation, we have around 1600 spectral counts. And fitting the models to it, the reduced chi-square value is very close to 1. The column density values are also consistent with each other. But here to notice that the line of sight column density is Compton thin, whereas the average column density is CT, and about 10 times more, showing a clumpy distribution just like the one before. Here also, the equivalent width comes much lower than 1 keV, and the covering factor is 1, showing strong obscuration. Thus, for this candidate, we can conclude that it is a partially Compton thick AGN with clumpy distribution of torus. Finally, for this source, we have excellent photon statistics for both soft and hard X-rays, and we can see that both the models give almost consistent values. Boras has best fit with photon index about 1.9 and reduced chi-square close to 1. Very interesting to note that both the line of sight and average column density is above CT threshold and almost equal to each other. The covering fraction is also very high, but didn't hit the upper bound like the previous two candidates. Also, FIT shows strong fluorescent line equivalent with above 1 kV. With all this information, we can conclude that this is a CTAGN with smooth distribution of torus clouds. So this is what we get after putting all the results in the Boras analysis in the parameter space of line of sight column density and average column density. The horizontal and vertical dashed lines mark the CTAGN threshold. This y equal to S line expose the smoothness of the torus clouds. The points line further signifies clumpiness. This block holds the CTAGN, whereas these two blocks cover the partial CTAGN sources, and this one exhibits Compton-thick AGN. So we inserted all the CTAGN candidates previously analyzed with Newstat data from these publications. From the 7 source I analyzed, these 3 came out CTAGN, these 3 partially CTAGN, and 1 Compton-thick, which I showed a few minutes ago. By overall analysis, we found only about 25% of the CTAGN candidates are found to be confirmed CTAGN, whereas 59% is partially CTAGN and 16% is Compton-thick AGN. Most of the CTAGN candidates were analyzed before using SwiftBAT and or only Swift XRT, which overestimated their column density. Using Newstar, XMM Newton, and Chandra improves the photon statistics, which overall helps us to recreate the census of CTAGN with more accuracy. Also, we found that about 86% of this population consists of clumpy torus. So this obscured AGN with high clumpiness needs more follow-up observations to monitor the long-term variability of line of sight column density. So a lot of work is still needed to be done on these sources. For my project, I will also study the infrared spectra of 7 sources, because as you can see, the infrared data shows direct results of obscuration than the X-ray picture. So a joint study of X-ray and mid-infrared band will produce a better understanding of the obscuration paradigm. Here I showed how the infrared spectra of a CTAGN is dominated by torus components over others. From the ACT fitting, we can find out several information like covering factor, column density, and more. Combining X-ray analysis with these results, we will have better understanding on these sources. This is our next goal. So as a summary, we analyze soft X-ray data using Chandra, XMM Newton. For hard X-ray, we use Newstat data. We fitted physically motivated torus models like MyTorus and Boras to expect and analyze these sources. From the 7 analyzed sources, 3 came out to be Compton-thick, 3 partially Compton-thick, and 1 Compton-thin. Adding my results to previous publications, we found that about 25% of them are confirmed CTAGN, 16% Compton-thin, and 59% partly Compton-thick. For our future work, we'll analyze the mid-infrared data with ACD fitting technique, and finally produce a joint analysis of X-ray and mid-infrared analysis of the obscuring medium. Thank you.
Thank you, Dhruv. As this talk has taken more than 15 minutes as a recorded talk, I will not allow any question here, but probably if there are questions, please take it on the Slack. And now I'll request Dipanweeta for the next talk.
Hello everyone, I'm Dipanweeta Bhattacharyya, a postdoctoral fellow at ISAN Mohali, and I'm working with Professor Jagjit Singh Bagla there. So the title of my talk is, where can we find the merged black hole in the black hole mergers? So to begin with,
This right here.
yeah, it's not.
Yeah.
Right.
On the present.
So to begin with, I will give a brief introduction to the problem which we are dealing with. Leading theory for how massive or supermassive black holes are forming is a hierarchical merging. Now, what is this hierarchical merging process? When binary black holes merge in dense clusters, their remnant can pair up with other black holes in the cluster also, so forming heavier and heavier black holes in a process which is called a hierarchical merger. Now, very densely packed environments such as nuclear star clusters or globular clusters, these are the very prime sites for the black hole mergers. But gravitational wave peaks might get in the way. So I will explain what the peaks are here. And when the black holes merge, they emit gravitational waves that of course carry energy and angular momentum. But these waves are not actually isotropic, so they are not emitted equally in all directions. So therefore, on the act of merging, impacts a peak to the merger product. Now, this is a toy model which shows how the peaks are basically forming. So it's an instantaneous snapshot of a gravitational wave recoil in an unequal mass binary. So we can see here two black holes are there, which are obviously of unequal masses. So in that case, smaller black holes is moving faster than the larger one. Therefore, it causes a gravitational radiation to be beamed more effectively in a particular direction. Now, there is a net ejection of the momentum parallel to the smaller black hole's motion. So this is referred to as a beaming kick. Now, therefore, the center of the mass also recoils in the opposite direction because of the conservation of momentum. So this is how the peak is. Now, it is important to note also that for all the observed black hole mergers, all are not unequal mass binaries. Therefore, the peaks in those cases is not expected to be very large, but there will be peak velocities there. So we discuss about the magnitude of the peak velocities, how this peak velocities are. But the typical peak velocities are estimated to be of 100 or 1000 kilometers per second. Now, we know that for globular clusters, the escape velocity of globular clusters is quite less, like almost around 50 kilometers per second, whereas for galaxies, it's quite high, it's around 1000 kilometers per second. So, if a black hole gets a big enough peak, it can leave the dense globular clusters is formed and emerge into the rarefied space, where it is less likely to undergo any further merger process. So, how typical it is for the black holes to get ejected from their globular clusters, and what does it mean by the theory of hierarchical merging? We are going to explain that. Now, the implications of the black hole peaks for the galaxy dynamics is also quite striking, because since the escape velocity in the galaxies is quite high, maybe the peaked black hole will not escape the galaxy, but it can shift from the center to some other place. So that will, of course, alter the galaxy core dynamics for at least 10 mega years. So that's why it is quite striking for the galaxies as well. Now, current gravitational wave detectors are not sensitive enough to detect the black hole peak directly, but it can be inferred from the gravitational wave that are observed because of the Doppler shift of the waves due to the peaks. Now, when a heavy particle moves to a sea of much lighter particles, it experiences a retarding force because of the exchange of angular momentum and the energy. Now, this is a process called dynamical friction, which can be intuited in two different ways. When a massive black hole, massive object moves through a cloud of smaller, lighter bodies, the effect of gravity causes the lighter bodies to accelerate and gain momentum and kinetic energy. And therefore, by conservation of energy and angular momentum, the heavier body will, of course, be slowed down. And since this is a loss of momentum and kinetic energy, this is called a dynamical friction process. It can be intuited in another way also. So when a large object moves through a cloud of smaller objects, the gravitational effect on the larger objects pull the smaller objects towards it. Now, then there exists a concentration of the smaller objects behind the object when already the larger object has moved a little forward. So therefore, the concentration of the smaller objects behind the larger body exerts a gravitational collective force on that larger object, which calls it drag force, and it slows it down. Therefore, in all the processes, we can see that it always causes the slowdown of the massive object, which is here the black hole. So we can assume that this process of dynamical friction will reduce the peak to black hole velocity, and when it starts moving out. So our aim is to study the different scenarios arising when it can reduce the velocity below the escape velocity or not. And if it doesn't come below the escape velocity, what will happen to the ejected black holes or globular clusters? So to form our model, we are considering this Klammer density profile for globular clusters, which is quite a common profile to take. And these are the parameters which we are considering here, where density, potential, and the distribution functions of the Klammer model are given here. A is the Klammer scale length, and rho 0 is the central transient. And as I mentioned, the dynamical friction, so we use the Chandrasekhar formula for dynamical friction here, where capital M is the mass of the black hole, which is the mass under consideration, and small m star is the mass of each stars in the galaxy, and Vm is the mass velocity of the black hole here, and F is the distribution function of the star in the galaxy, and lambda is the Coulomb law variable. So we solve this equation for Vm, which is the velocity of the peaked black hole, as a function of time using the Klammer density model. So there can be three possible scenarios in case of globular clusters. First of all, when the peak velocity goes down below escape velocity before one crossing time, it will not come out of the globular cluster. Therefore, it will be staying in the globular cluster itself. So this is the first scenario. Now, second scenario can happen that when the black hole escapes the globular clusters, but then it end up crossing the bulge after getting ejected from there. In that case, the dynamical friction within the bulge will trap it. So we expect a population of intermediate mass black holes in the bulge. Now, black hole misses the, another case can be possible that where black hole misses the bulge and becomes a halo object. So then it can be expected to gradually slow down due to dynamical friction during the disk crossings and gradually will be trapped in the disk and then sink towards the bulge. So these three scenarios are possible. So we'll try to find out the velocity limits for these scenarios. So now we come to the results, whatever we have found. This is the velocity of the kicked black hole for a general case as a function of time. The time has been considered as a unit of crossing time. So we can, as I already mentioned, that the peak velocities can be around 100 kilometers per second. So we are taking here around 80 kilometers per second. It starts from, and then for three different masses of black holes, we see how it goes down within one crossing time. So here we can see for higher black hole, higher mass black holes, it goes down much earlier compared to the other cases. So therefore, higher mass black holes tend to slow down early. Therefore, it indicates that the higher mass black holes have less probabilities to be ejected from the system. Now I'll show the density dependence of this thing. Since dynamical friction is created by the cloud of the smaller particles, therefore obviously density will be a good factor which will show the effect on the results. So here first of the first plot in the left, it shows the velocity at one crossing time as a function of density for the black hole. So we can see as the density increases, the velocity goes down as it is expected. And the second one is the plot of velocity as a function of time for three different density values. We can see for higher density, the value goes down quite early, which is obvious because the density higher, the dynamical friction will be higher compared to that. So therefore, the velocity will decrease earlier. So these three are done for 100 to 300 solar mass per parsec cube. Typically, the central density of globular clusters is around 100 to 1000 solar mass per parsec cube. So we are taking these three values here for our calculation. Now I come to the first case. As I mentioned, the three possible scenarios. First one is the no escape scenario. So for when the black hole will not escape from the globular cluster, that means it has reached below the escape velocity before one crossing time. So here we are considering a boundary case where we are assuming that at t equal to 1 t crossing time, it just reaches the escape velocity value. So the left plot shows the maximum peak value possible for which at t equal to 1 crossing time, it will be exactly the escape velocity of the globular clusters. So we can see the plot as a function of mass, and higher the mass is, higher is the peak velocity. And second plot shows the peak velocity and the escape velocity ratio as a function of mass. So that is also increasing with respect to the mass. And this is the plot for the velocity as a function of time for these three masses in this no escape scenario. We can see here at t equal to 1, t by t cross equal to 1, it reaches exactly 1. That was our condition here. So we can see the higher mass black hole starts from higher velocity, peak velocity, then it reaches to escape velocity. So this is a no escape scenario. That means the globular cluster will trap the black hole there. Now, if the second case happens that it gets slightly higher velocity than this, therefore it will come out of the globular clusters. Then it will get trapped in the bulge itself. Since the escape velocity of the bulge is quite high, therefore it will not escape the bulge, it will get trapped there by the dynamical friction of the bulge. So I'm not discussing the case here. I discuss the third case when it escapes the cluster and lands up in the halo. So if the black hole velocity doesn't come below the escape speed within one crossing time, it will escape the cluster. So here we are considering a very simple case. Here we are assuming that the bulge center is at F1 and the globular cluster which is ejected, it does at the maximum distance point, that is R max. So from there it is coming. And so we are calculating R minimum here, which is the distance of closest approach. And if it is more than the radius of the bulge, that means it will escape the bulge. And if it comes within the bulge radius, it will be plugging into the bulge. So from here, we are calculated the A into 1 minus epsilon. A is the semi-major axis and E is the eccentricity of the elliptical orbit here. So we found out
Dipanweeta, you have 3 more minutes.
okay, fine. We found out the scenario when the distance of the closest approach is more than the radius of the bulge. Therefore, this ejected black hole won't enter the bulge and probably ends up in the halo. So the eccentricity is given by the central mass formula is equal to square root of 1 minus L square by mk. So from there we solved this. And this is the plot which shows the escape velocity, I mean the velocity with which it escapes the globular cluster as a function of mass. So we can see it increases function of mass as expected. So this will be the velocity at which if it escapes from the globular cluster, this will end up in a halo and eventually it will sink towards the bulge later on. Now, actually, we are going to do simulations for detailed calculations. So for now, I'm just showing one data detected by LIGO just to show with our results is compatible with the observations also. So in a recent paper, Dhrubojyoti 2022, for this particular gravitational event, they have determined the peak velocity for the globular clusters lies within 60 to 100 kilometers per second. And the final mass from the LIGO data is 63.4 solar mass. So here we are showing the plot for the no escape scenario, and we can see that our plot lies exactly in between these 2 points. Therefore, if the velocity is less than this curve, therefore it will get trapped in the globular cluster itself. And if it is more than that, then it will escape the globular cluster and land up in the bulge because it will be trapped in the bulge. It is not quite high. But for in case the escape velocity and peak velocity is quite high, like 1,000 kilometers per second or something, then obviously it can escape the galaxy even. So for that is called super peak. So that in that case it can escape the galaxy also. So yeah. So to summarize, we have studied the motion of the peak black holes in globular clusters when their speeds reduce because of the dynamical friction, and we have found the higher mass black holes tend to slow down earlier compared to the lower mass ones. And also the speed is highly dependent on the density, which is an obvious result. And we studied the boundary case when it just manages not to escape from the cluster, and also found the maximum peak velocities in those cases. And then we studied the case where the black hole gets ejected from the cluster but escapes to enter the bulge and rather ends up in a halo. And we're exploring the scenarios using the in-body simulations, and these results can be compared to the findings of LIGO for different marginal events and the peak velocities to know the most probable scenario, which can predict the final position of the remnant black hole in globular clusters. Thank you.
Thank you, Dipanweeta, for wonderful talk. I will allow one question. So first from hall, if there is a question from the hall. Okay, if not, any online participant, if he or she has a question, please raise your hand.
Yeah, I have a question regarding this skin technique.
Yeah.
So did you consider the effect of the disk soaking? So when globular crystal is passing through a disk?
No, we have not considered that.
Okay.
Okay, then we'll move on as we have a less time.
Thank you.
Thank you very much, Dipanweeta. So now we are moving to our fourth talk. So our next talk is by Habeeb Rahman. Habeeb, I'll give you a warning around 11 to 12 minutes.
Yeah. Hi, everyone. I am Habeeb Rahman from University of Calicut, and happy to be here for this talk. And the topic I am going to discuss with you is the relation between particle dynamics of AGN jet and X-ray spectral curvature. This is a part of my PhD work, and my supervisor is Professor C.D. Ravi Kumar from University of Calicut, and the work is doing with collaborator Sundar Sahayanathan from BARC. So let me give a short introduction about active galactic nuclei, which is a compact region at the center of galaxy with high non-stellar luminosity. And this agent is powerful than the nucleus of normal galaxies. From the figure, you can see that the powerful emission from the central region of AGN overshine the rest of the part of the galaxy. And we have a strong evidence that this powerful emission is due to the presence of supermassive black hole at the center, having mass between 10⁶ to 10⁹ solar mass. And there is a special feature called a collimated emission, we will call it as a jet. And we are looking into a special class called blazar, which are the luminous class of AGL, that the jet is aligned towards our line of sight, then we will call it as a blazar group. Otherwise, some other groups are there. Anyway, we are not going into that. We are discussing about this blazar and the modeling of emission, that's jet emission. We are going to discuss. So for this modeling, we consider two zones in the blobs. One is acceleration zone, other is cooling zone or region. Acceleration region is there, one is cooling region. So we are considering the synchrotron emission from this cooling emission zone, that is electron we are considering. So the electrons entering into this acceleration zone will accelerate in that region, and these accelerated electrons will inject into the cooling region where the emission process is happening. So this modeling can be do with this equation, which is given in Kirk et al. 1994. The first term in this equation represent the number density changes, evolution of number density with respect to time, and the second term contains two parts. One is this part. This part is represent the acceleration rate E by tau A, where tau A is the acceleration time scale, and the second term zeta E square represent the emission, and the right hand side this Q delta function represent the injecting particle, this coming particle for the acceleration process, and this last term N by tau E represent the escape from that region, acceleration region represent the escape region. So we have a relation which connecting this escape time scale from the acceleration region due to the spatial diffusion. So the relation given in Shelley scales 2002, which is like this: tau E escape time scale will be proportional to E by E0 raised to Q raised to minus 2, where E is the energy, E0 is the initial energy, and that Q represent the index of magnetohydrodynamic turbulence spectrum. We will discuss about that. And there is a paper in 2020 by our group member Goswami et al. They considered the electron escape from this acceleration zone in this form, in this manner. That model is called energy dependent diffusion model, and they parameterize it as the escape time scale is proportional to E by E0 raised to 1 factor kappa. Its energy dependence parameterized to kappa. So by using this assumption, they solved that kinematic equation for this acceleration region and for this emission region, and they got some numbers. That's the electron spectrum number n of E comma t. They considered the equation which is steady state. Therefore, first term will not be there, no dependence on time. So that solution gave this result. There is some mathematical steps are there. So their model demands that the model parameter psi and this kappa should be, they should show a linear correlation. That's demand from that model. Anyway, they showed it, they analyzed this result, this mathematical equation they put into some observations, that is in Markarian 421, and they successfully produced this linear correlation, where you can see some blue data points and some red. This blue represent for the combined Swift and New Star observation, and for the red represent New Star alone data. So this linear correlation is supporting that their model is acceptable, and along with that they check the correlation between the flux and this kappa, and for this flux plot they are not getting such a well correlation. Here also you can see that blue data points and black one, this blue represent for this combined Swift and new star observation, and this black for the new star alone data. So where the role of curvature is coming is, that's a question maybe in your mind. If we solve this kinematic equation, you will have a final product, final answer will be there. So in that spectrum, in that emission spectrum, this kappa term will represent the curvature of the spectrum. That's why the curvature, X-ray curvature is related to the dynamics. So where the dynamics is coming, that's the next question. So we can relate. In previous slide I show that two relations for this tau E. So if you compare these two relations, you can equate that Q minus 2 and that minus kappa. From that, you will get the relation between this kappa and this Q. So for different values of Q, we can evaluate the corresponding kappa value, means this kappa value represent for the curvature. So by putting different values of Q, there is different values of Q for different types of diffusion modeling. For hard sphere diffusion, we will have some Q value. For colmography, we will have some other Q value. So giving that value into this equation, we will get the corresponding kappa value. That's why we are getting different vertical lines here in this graph. So the problem is here, there are some points beyond this Bohm limit. This one for kappa is equal to 1 corresponding to Bohm diffusion. There is some point, 3 or 4 points are there beyond this Bohm limit. So this is unphysical. Beyond Bohm limit, no point should be there. This is unphysical. That is the issue related to this work. So we are going to address this problem. For that, we considered energy dependent acceleration along with the energy dependent escape. Previous model only considered energy dependent escape only. So here we consider energy dependent acceleration. So by introducing that change, that modification, we are able to take all the point within the Bohm limit. That is the result we have. Okay, you can see that different hard sphere and Kolmogorov, Karishna and everything shifted. Initially, that Bohm was at the line 1. When kappa is replaced by kappa minus beta by doing that mathematical step. So everywhere 2 times shift will be there for this different diffusion process. I will discuss the mathematical step very briefly. Okay, anyway, this is the result we have. So we plotted that previous flux plot, again we replotted. There also we are able to take all the point within that limiting conditions. Okay, then how we did this modeling, there's a mathematical step behind that. We consider the steady state equation. This is the steady state equation for the acceleration region, and the first time will not be there because of steady state equation. And we are considering injection time. Some electrons are injecting into the acceleration zone. That is monoenergetic injection, having some energy less than E0. That's why the delta function was there at first equation, kinematic equation, delta function was there. That also will go on. And remaining things are here. This is a steady state equation, acceleration region. So by solving this equation, we will get the electron spectrum in acceleration region will be like this, where this zeta 0 will be the ratio of TA by TE at energy equal to E0, this zeta 0. So if we compare this result with the previous result of T. Goswami et al., which is just replacing that kappa value, energy dependent escape will replace by this kappa minus beta. Functional form will be same. So our value should be same. So we are just replacing that kappa to kappa minus beta. That is the main difference. Okay, then.
Habeeb,
So
you
this,
have 2 minutes. You have only 2 minutes.
Okay, yeah. So this acceleratory electron will inject into the cooling region. Then we will solve equation in the cooling region. Finally, we will get this equation, electron distribution in cooling region where the cooling process is happening. So the flux can be calculated by putting this NC, number of electron in cooling region, into the flux equation. That's some mathematical steps are there. This is the equation. So initially I told there is a relation demands this mathematical modeling linear correlation between psi and kappa minus beta. So this is the equation, psi equation is there. So if you take the log in both sides, you will get a linear equation. This is the demand from this model. It should be the correlation should be a linear. So I am going a little fast. And I also said that turbulent spectrum and this MHD magnetohydrodynamics in the vicinity of shock related to the scattering process inside this acceleration region and between this acceleration and cooling region. So that is responsible for this diffusion process. And we have the turbulent energy spectrum WK proportional to K raised to minus Q. For that different Q values, we will have different diffusion processes, Q equal to 1 Bohm diffusion. So what we done is that we considered the dependence. The modification is that tau A proportional to E by E0 raised to kappa, tau E proportional to E by E0 raised to beta, the corresponding constants are there. And from Schwartz spectroscopy in 2018 and trauma care, we have the relation acceleration time scale related to this Q value and escape time scale related to this Q value. So by comparing this to kappa and 2 minus Q and beta and Q minus 2, we will get this kappa minus beta like this 4 minus 2K. Initially it was 2 minus Q. Now there's a multiplication of 2 came because this modification. And corresponding kappa value we can evaluate by substituting Q value in this equation. So and we additionally we applied this model into Markarian 501. There is few number of observations are there. That's only seven observations are there. And here also it's showing linear correlation between psi and kappa minus beta. And for flux, we didn't expect such correlation. There are also previous models, so that correlation was very weak. Anyway, every point within this Bohm limit, that's the result we have. So this is a modification as a summary conclusion. This is a modification of previous model ETD4, and here we expressed the energy dependence in parameter given by Goswami et al. As a combination of acceleration escape parameter kappa minus beta, and this work is applied in this model is present marker in 421 and marker in 501 using shift XRT and user observation. And this was an attempt to probe the particle dynamics in blazar jet through X-ray spectral curvature. Yeah, that's all.
Thank you, Habeeb. We'll only take one question if there is very urgent one from the hall or from the online audience.
Hi. So,
Hi.
what do you expect? Like, this is a universal. Like, we can apply this physical model that you people are developed to all the blazar, or is there any criteria like we have to use this for this?
For a source criteria, yes.
So
I saw your paper.
Yeah,
like similar to this.
Yes.
Okay. Anyway, we are applying this model into HBLs only.
Yeah, your BLX sources. Till now you used Merton 421 and 501, right?
HBL sources. For these two sources, we are getting the result perfectly. But I think I was looking into the light curve of which observation is satisfying this model. Till now, I didn't find any special feature. But for these two sources, it's okay. We have to test whether it is any common feature.
I think the source we saw some curvature.
Yeah.
So specifically for that type of source. Like this model is specifically for that type.
For HBLs. IBL and LBL we tried, but it's not working.
Yes, obviously.
It will not work. Curvature is that much curvature is not there.
Not there, yeah. Okay, thank you.
Okay, yeah.
Thank you, Habeeb. Yeah, now we'll move on for the final talk by Savithri. Savithri, I will warn you around 12 minutes.
Hello everyone. I'm Savithri. I'm a postdoctoral fellow at Christ University, Bangalore. So today I'll be talking about the optical and gamma ray variability in the blazar, PKS 122+216. So this is the plan of the talk. I'll start with a brief introduction to blazars and the motivation of the work. So blazars are a subclass of active galactic nuclei, which has highly collimated jets that point very close to the line of sight of the observer. And the emissions from blazars are non-thermal in nature, and they emit radiation from radio to very high gamma ray energy, very high energy gamma rays, and they are also often highly variable. And considering the spectral energy distribution of blazars, it has a double hump structure. One low energy component which peaks in the radio to X-ray band, and one low energy component which peaks in the radio to X-ray band, and one high energy component that peaks usually in the X-ray and gamma ray band. And this low energy component usually arises due to the synchrotron radiation that is produced inside the jet, and whereas the high energy part of the SED is produced by the inverse compton scattering process, which can be either synchrotron self-comptonization or external compton scenario. So in the external compton scenario, the seed photons for inverse comptonization can be arising from either the accretion disk or the BLR or the torus regions. So blazars can be broadly classified into two categories. One is BLR objects and another one is flat spectrum radio quasars. And both of these objects are continuously detected in gamma rays. And the gamma ray emission from BLR objects is usually dominated by the synchrotron self-comptonization scenario. Whereas in the case of FSRQs, the gamma ray emission is dominated by the external comptonization scenario. And based on the optical spectrum, they show different features, both BLRs and FSRQs. And BLRs usually show a featureless optical continuum, whereas FSRQs show very strong optical broad emission lines in the optical spectrum. And this broad emission lines in the optical spectrum arises from the BLR region by the photoionization of the gaseous clouds in the BLR region by the accretion disk radiation, by the radiation of the accretion disk emission. So in the case of blazars, actually the optical continuum is dominated by the emission from the jet. So, and we do not have a direct view of the accretion disk in the case of blazars. So in that case, the broad emission line flux actually provides us an indirect information on the disk emission. So through any variability from the BLR emission, we can track the variations in the thermal emission from the disk. So therefore, the correlation studies between the BLR emission and the gamma ray emission from the jet, through these correlation studies, we can actually probe the connection between the jet and accretion power, which is still an unsolved issue in the field of AGN, that is the disk-jet connection in AGN, basically. So motivated by this, here we study the long-term optical and gamma ray variability and the possible correlation between this emission in one of the FSRQs, PKS 122+216. And the target PKS 122+216 or 4C21.35 is a bright FSRQ that is found at redshift 0.043. And the source is detected in gamma rays as well as in other energy bands. And it has also observed to show very high energy emission. And it has also been reported to be showing various flaring activities, multi-band flaring activities at various epochs. Besides this, the optical spectrum of the source also shows strong emission line features. And using these optical spectra, they have previous studies have reported a black hole mass of roughly 1 billion solar mass in the source. So for this study, the study requires data both in the optical and gamma ray bands. And the source has been continuously monitored with in gamma ray band and optical band with Fermi and the ground-based optical observatory, Steward Observatory, that operates in the energy wavelength range of roughly 4,000 to 7,500 angstrom. And for this study, we collected spectroscopic data from the spectropolarimeter detected with the spectropolarimeter on Steward Observatory. And for gamma ray data, since it has also been continuously monitored with Fermi, we collected the data, gamma ray data from Fermi, Fermi-LAT telescope, and we obtained the light curves with Fermi tools and Fermi 5. And as I said, we are more interested in the optical emission line, broad emission lines, as well as from this object. So we collected publicly available data from Steward Observatory, and these are the different spectra observed with Steward Observatory from 2010 to 2018, roughly spanning 8 years. So these are there are more than 300 spectra, optical spectra available for the source, and these are different spectra for this time range. And to identify the broad, the strong emission lines in the source, we created a mean. We plotted a mean spectrum from this observations, and this is the mean optical spectrum for the source obtained from this observations. And this red line is the observed spectrum, whereas the blue line is the degradant spectrum. And here are the identifications of the prominent emission lines in the source. And here the strongest line among this is the H beta line. But this emission region is affected by the atmospheric features. So we avoided this region for further studies. And we are selecting this H gamma emission region, which is the strongest among other emission lines. And we are focusing on this region for further spectral analysis. So our idea is to estimate the emission line flux, the H gamma emission line flux, which can give information on the disk emission, and also the continuum, the optical continuum from the source. And for this, we analyze the optical spectra from this optical spectra of all the observations from the sources for the local region, local spectral region near this H gamma emission line. So this is one of the examples of the such a spectra, local spectra. Here we fitted the spectral region with power law model to describe the continuum emission, and a Gaussian line to model the broad emission line, the H gamma emission line. And here is the spectral fit and the residual for the spectral fitting result for this particular observation. And after fitting this spectra, we estimated the flux continuum, continuum flux, optical continuum flux, and the broad emission line flux, as well as the related parameters. And this is the light curve showing the best fit parameters for various spectra. And the left panel shows the parameters, flux and parameters for optical continuum that is obtained from the power law model. And the right panel shows the H gamma emission line parameters. So these two panels shows the continuum emission for a narrow region local to this near this H gamma emission line. And these two panels shows the power law index as well as the amplitude of the power law. And here, this shows the Gaussian flux, that is H gamma emission line flux, and the FWHM of this emission line, and also the position and the corresponding equivalent width of this emission lines for the variation of the equivalent width over various time, over this time span. So then we find the correlation between the relationship between various parameters, various optical parameters with the continuum flux. And this is the excuse me. This is the flux ratio, the variation of flux ratio with the continuum flux, and this is the variation at 5,442 and 44 angstrom and 6,644 angstrom, 64 angstrom, and this is the variation of equivalent with the continuum flux, and here is the variation of H gamma flux with the optical continuum flux. And here we can, in the last panel, we can see that the H gamma flux, that is the emission line flux, is nearly constant, doesn't vary much. It says that the thermal disk emission is nearly constant. It doesn't have it doesn't show any significant variability in this particular source. And also, this is also supported by the variation of the equivalent width with the continuum emission, which shows a inverse correlation, trend of inverse correlation between the equivalent width and the continuum flux. And here, in the first plot, the flux density ratio also decreases as the flux increases, which shows a redder than brighter behavior. And this indicates the dominance of jet emission over the disk emission in the source as the source brightens, and this is the typical behavior that we expect in the case of FS cycles. So,
Savithri, you have 3 more minutes.
Okay. Yeah, so here, after this optical analysis, we collected the gamma ray data and we analyzed the light curves of optical continuum flux, broadline emission flux, as well as the gamma ray flux. And these are the light curves showing these 3 components. And this panel shows the variation of gamma ray flux, the H gamma flux, that is the broad emission line flux. And this is the optical continuum flux for 2 different regions. And here the last panel shows the gamma ray flux. And the various symbols shows correspond to various observation cycles in optical data. There are different various observation cycles, and there are seasonal gaps in the data. And various symbols shows the observation cycles for of the Steward observatory observations. And in order to find the connection between the optical flux, the optical continuum and line fluxes, and the gamma ray flux, we carried out a cross correlation analysis. And since the data is unevenly spaced, we followed this pi DCF analysis and to estimate the correlation between the between these fluxes. And this panels show the cross correlation results from pi DCF for the gamma ray emission as well and the optical continuum flux. And this panel shows the cross correlation for gamma ray and H gamma flux. And here we observe a positive correlation between gamma ray emission and continuum flux, which is with a DCF value around 0.5, and this very significant at 3 sigma level. But we also tried to get if there is any time lag, it shows positive correlation over a broad range. So we tried to find if there's any to estimate the time lag of this correlation using bootstrap method. And here is the result for the distribution of time lags obtained with the bootstrap simulation. And here we find that the time lag is consistent with 0. That is, the emission region is the emissions are positively correlated with no time lag, which means that the emissions could be rising from the same regions. And also, one thing we should note that these light curves are suffered by observational gaps. So the time lag estimate that we obtain could be suffering from the observational gaps that is present in the optical data. So yeah, so we need much more better high cadence monitoring of long-term monitoring of this of blazars in optical and gamma ray bands to get better constraints on the time lag of this observation of this correlation. And also we have also checked whether there is any correlation when the flares are not present in the data, because here we are seeing different flares in both optical and gamma ray light curves. But so we tried by the correlation between these emission bands by removing the flaring episodes, and in that case we did not find any strong correlation between these 2 emission components. And another cross correlation result is for H gamma emission line and gamma ray emission from the source. And here we did not see any significant correlation between these 2 emission components. Since H gamma emission, as I said before, since H gamma emission is an indicator of the disk emission, the lack of correlation between these 2 components points to this favors the origin of disk photons. The the disk photons as the seed photons for the external quantization scenario in the source, which can also mean that, which also indicates that the the seed photons for external quantization in the source is contributed by the torus or BLR region present in the source. So summarizing the results, we study the connection between the optical continuum, broad H gamma broad emission line, and the gamma ray emission from the from PKS 122+216 using long-term optical and gamma ray observations. And we find higher variability in the optical continuum than the H gamma emission, and inverse correlation between the H gamma equivalent with an optical continuum flex and a redder when brighter behavior expected in the case of Hepz vacuums. And the cross correlation analysis between these emission components provides a strong, significant positive correlation between the LAT and optical continuum flex, gamma ray and optical continuum flexes. And we did not observe any kind of correlation, any significant correlation for when we remove the flaring episodes. And also, there is a lack of correlation between the gamma ray flex and H gamma emission lines, which dismisses the disk origin of seed photons for the external quantization scenario in the source, which also indicates that the gamma ray emission zone is the source is apparently located in the edge of the BLR or torus rather than the innermost regions of the source. So this work has been submitted to FG, and we are the revision is in progress. And in future, we plan to study a sample of Hepz vacuums and to carry out similar studies and explore the disk-jet connection in blazar. Thank you.
Thank you, Savithri, for very good talk. As we are late, I will allow one question on the urgent basis. So
Hi.
if there is,
Hello. Yeah.
please go on.
So why did you choose this source?
Yeah, this is one of the bright FSRQs, and it has coordinate monitoring in both gamma ray and optical.
But it doesn't have a strong H gamma emission line region. So
it is significant. It is pretty strong, and yeah, and this is not affected by any atmospheric absorption features. So we could constrain the optical the flex of the source and the continuum separately.
Okay. And which region you have? You have eliminated those flaring regions, right?
For cross correlation analysis,
Yeah. So
to see whether there's any correlation in the quiescent state. So,
okay, so this is a quiescent state light curve?
No, this is the total light curves, and at various episodes, it is showing flaring in both optical and gamma rays. So we try to remove this flares so that we get the light curves in the quiescent state and check whether there is any correlation, and we did not find any correlation.
Thank you.
Okay, thank you very much. Thank you, Savithri. And I thank all the speakers for a wonderful talk. And I also thank audience for a patient audience for listening them and a very interesting conversations. So thank you very much. Now I will close the session. Thank you very much for being here.
Thank you, sir, for joining with us.
Thank you.
Hi.